days I seen my best. Need be lay me to rest. Smoke, drink, relieve my stress. Hard times, they got the best of me, I guess.
In this video I will talk you about Doppler effect, which explains what happens when the sound source and the observer are moving relative to each other. In the first case we have the source moving and the observer is standing still. It's quite easy to see from this figure what happens to the sound waves in front of the truck. The truck will chase them, and this results into the sound waves being compressed, which means that the frequency increases. On the other hand, behind the truck, the sound waves get stretched, and this is the case when the frequency decreases. We also have the case when the fire truck is standing still and we have an observer moving instead. Now, as the observer moves towards the fire truck, it will cross these wave crests faster than it usually would, and this also results into frequency being increased when they are moving towards each other. And if the observer is running away, these wave crests will end up chasing the observer. But because the observer is moving away, it takes a longer time for two consecutive wave crests to reach the observer. So in this case, the frequency decreases. All of these four cases have to be treated a little bit differently mathematically. I won't go through the derivations because that's being carried out in the book, but let me recap those, and then I will show you how to calculate the frequency shift in all these different cases. So first of all, let's think about the first case when the source is moving towards the observer. In that case, the Doppler shifted frequency f prime is expressed as follows. It's the V sound divided by V sound minus the velocity of the source. Because the denominator is less than the numerator, this whole quantity is larger than 1, which means that the frequency increases, and that is consistent with our description here. Now, if we have the case that the source is moving away from the observer, the shifted frequency looks similar. You have sound velocity, source velocity. The only difference is that instead of minus, we have plus. Okay, what about the cases number 3 and 4? When the observer is moving towards the source, the shifted frequency is the original frequency, if you will, times sound velocity plus velocity of the observer divided by sound velocity. Again, this quantity is larger than 1, which leads to the Doppler frequency being larger than the original frequency. And this is consistent with what I explained earlier. And then we have the last case when the observer is running away from the source. Original frequency, and then we have in the parentheses speed of sound minus velocity of the observer divided by velocity of the sound. Let's complete this figure by pointing out that this case refers to this guy standing behind the moving truck, running away from it. Now, we can combine all these four cases into one single formula that will serve all our purposes when we have to calculate the Doppler frequency f prime. The original frequency when nothing is moving is f, and we have speed of sound plus minus the velocity of the observer. Let's make that again. Divided by a velocity of the sound minus plus velocity of the source. About these signs in just a sec. So in order to use these equations for all our calculations, we need to define two things. One, which term is zero. For example, in this case, when the source is moving, it means that the observer is standing still. So in that case, the velocity of the observer would be zero. Whereas when the observer is moving, the source is standing still, and this term would be zero. Once that has been decided, we have to think which signs should we use, the plus minus here and the minus or minus plus here. The rule is if the source and the observer are approaching each other, we will use the upper signs. If they are running away from each other, we will use the lower signs. By upper signs, I mean we would pick plus here and minus here, and if we have the case that the observer and source are running away from each other, we would use the lower signs. We would pick minus here and plus here. Now let's work a couple of examples that were given in the textbook.
I'm more than a man. I died and I rose again. I left these hoes in my hand, just so you know who I am. An alien, extraterrestrial, ET's a mini-me. You understand? Look what I did. Smoke like a chimney. Then
In exercise G, we are supposed to calculate the Doppler shifted frequency when we are moving towards a police car that is blowing its siren. So, the first case, when we are approaching the police car, we immediately can say that the police car, the source of the sound, is standing still, so the V source is going to be zero. And because the observer and the source are approaching each other, we're going to use the upper signs. So f prime will be original frequency, or the rest frequency, if you will. We pick the upper sign. and the source velocity was 0, so we don't have to include that. Okay, the original frequency 1600 Hertz. The velocity of sound in room temperature 343 meters per second, and our velocity is 25 meters per second. This gives us 1717 Hertz approximately. Okay, what about the case when we are moving away from it? Again, nothing changes in terms of the fact that the source is standing still, so this term is again 0. But now, because we are running away from it, we will use the lower signs. So we pick the minus from here. We have f prime equals v sound plus v observer, minus v observer divided by v sound. Plug in the numbers. 343 meters per second minus 25 meters per second. Let me make that clear. That's a plus. Divided by 343 meters per second gives us 1483 Hertz. In exercise H, we were asked how fast would a source have to approach an observer for the Doppler shifted frequency to be twice the original frequency. Let's start by picking up the correct equation for our case. We know that the source is moving, so in that case the observer velocity is 0. And now, because these two objects are approaching each other, we will use the upper signs. So we'll pick the minus from there. So now let's rearrange this a little bit. So we will move the original frequency from the other side to the left. And this will give us the following. And the requirement was that the Doppler shifted frequency has to be twice the original frequency. So this is where we work on from now. Let's solve this equation. So we get v sound equals 2 times v sound minus 2 times v source, and rearranging gives us 2 times v source equals 2 times v sound minus v sound, which simplifies to v source being v sound divided by 2. So the source velocity is half of the speed of sound. And in that case, that would be the option A.
Can I get a motherfucking witness?
These days I see my best.
So,
Need be laid